All right, so we got to understand what power is, and in general, that's really all you need to know. Okay, there's not going to be any like massive calculations to do with power. It'll just be checking kind of that you understand what the concept of power is. Okay, so understand the relationship between power, force, and velocity. Not really. Okay, I'm going to talk about it, but it's not something you're going to get tested on again. You just really need to know what power is. Okay, and learn that power relates to how quickly work can get done, not how much work can get done, right? Because if I have two machines that do the same job and one is far more powerful than the other, they can do the same amount of work. It's just going to take the less powerful machine a lot longer to do it. Okay, so I mean, if time is a factor, then you probably want the more powerful machine. Okay, if time isn't a factor, then a less powerful machine will do the same amount of work. It will just take a longer period of time for it to do it. That's the key concept for power. Okay, power is how quickly work gets done, okay, as opposed to how much gets done. Okay, so if we're looking at like a kind of situation like this where we got these two like 1996 Honda Civics, okay, one that you could buy in the showroom in 1996 and one that would be in like the original Fast and Furious movie, which like came out before you were born, probably close to it. Anyway, one is more powerful than the other. Can they both get to 60 miles an hour? Yes, they can, but one can do it more quickly than the other because it has a more powerful engine. Okay, maybe it's been chipped and a turbo thrown on and a big blower or whatever. Okay, it's got more power. Okay, and so as a result, it can do the same amount of work in a shorter period of time. Okay, they can both get to 60. They're both capable of that. Okay, but one will do it more quickly than the other. All right, everybody all right with that idea? Okay, so essentially then, all power is, okay, power is work divided by time. Okay, that's all power is. It's work divided by time. The faster you can do the work, the more powerful you are. Okay, so that also means then that it could be force times distance divided by time. Okay, and if that is true, what's distance divided by time? Speed. So it could also be then that power equals force times speed. There's a whole bunch of different ways to calculate power. You won't have to use any of them. But at least now you know that there are many ways to do it. Okay? In general, again, we just need to understand, okay, this idea. So it's work divided by time. Okay, that's a joule per second. The units for power are joules per second, which we abbreviate as watts. Okay, so when you're looking at like a light bulbs are often rated in watts. Okay, that tells you how many joules they use every second. So if you have a conventional incandescent 60-watt light bulb in your house, it is using 60 joules of electricity every second. All right. Can you find a more efficient version? Right. You could put one of the CFLs, that's those like coily ones, okay, and it would do the same. It would only take 13 watts. Okay. It can emit just as much light, but use less energy. Right? It's more efficient. It doesn't make as much heat. Okay? Or you get an LED, and I think you're going to replace them with an LED of like 6 or 7 watts. Okay? So they use way less energy. Right? They produce just as much light. Right? These two machines here could also do the same amount of work. Okay? This is Grand Coulee Dam in Washington. Okay? It generates electricity through the force of falling water. This is somebody's like old flour mill water wheel. It turns a turbine essentially using the energy of falling water. If I ran this one for 1 second and this one for 1,000 years, they could probably do the same amount of work. Okay, but obviously this one is more powerful. Okay, it has a much larger river behind it and many turbines, whereas that has one. No, it's the same kind of watts. Actually, I'm going to go over that here in just a second because I mean, I actually when we were shopping for a car a few years ago, one of the places we went to actually had the power output in watts, and it was the most meaningless number I think I've ever read. Okay, because I mean, when you're shopping for a car, I want to know how many horses. right? I don't, watts, like, okay, is that like good? Is that more than my blender? Like, I don't know. That blenders and hair dryers and light bulbs are fine to measure in watts, but I need to know how many ponies are under the hood when I look at a car. Watts doesn't mean much to me, okay? So yeah, there is obviously watts and horsepower are measuring the same thing. Okay? Horsepower is just the imperial units for it. And the reason we came up with the units of horsepower was, what did the internal combustion engine replace? Horses. Okay? And so what people did is they actually measured the power of a horse. How much work can a horse do in 1 second? Okay? And then they were able to calculate how many horses will this tractor you're going to buy replace. That's what farmers wanted to know. Okay? If I'm going to send horses to the glue factory, okay, then I need to know how many I can send when I buy this tractor, okay, because I need to know how many horses it's going to replace, right? So that was the whole reason behind that, right? All right, so we already talked about this here. If power is work over time, then it's force times distance over time, which means it's also force times velocity, okay? And again, you're not going to be asked to do any calculations with that, so okay, we don't even need to go over it. All right, so on this note here, okay, the unit of power in the imperial system is the foot-pound per second. Okay, I don't know, foot-pounds, whatever. Okay, and although the familiar unit of horsepower is frequently used in its place, the power of one horse is 550 foot-pounds per second, which is the equivalent of 746 watts. Here's how they figured that out. They essentially kept adding mass over a pulley attached to a horse. And as long as the horse could pull it at 1 meter per second, then they were able to kind of calculate how much power he had. So they had a 750 Newton object hanging over the pulley. If he can pull it at 1 meter per second, then they add more weight, right? And so on and so on. When he couldn't pull it at 1 meter per second, then they were at the limit of the horse. 1 horsepower is 746 joules per second. All right, so when he's lifting this here, that's what it ends up being. Okay, everyone all right with that? So it's a Newton meter per second. That's a joule, or sorry, a watt, sorry. All right, so 746 watts means if you put a horse on a treadmill attached to a generator, he could run approximately 700-watt light bulbs. Seems like that's a misuse of a horse, but whatever. Okay, that's about the equivalent of what it could do. All right, so if we have like an alcohol-fueled funny car, okay, similar kind of idea here. It would have many horsepower, right? We could figure out how many if we wanted to, but again, we don't have to do these calculations, so we're just going to skip that. Okay. All right, this is the big thing to remember. Power is work divided by time, and the units for power are watts. Okay, so if your hair dryer dies and you got to go buy another one, okay, you look at price probably first. Everything's price first. And then you would look at how much power it had. Okay. If you're like always in a hurry, then you probably want like a 1500-watt hair. I don't know if they come that, but whatever. 1500-watt hair dryer, right? That means it's going to use 1500 joules per second. Maybe that sets your hair on fire. I don't know, but it would be dry. Okay. Or maybe you look at something that's a little, if you're not wanting to damage your hair, you want to dry it a little bit more slowly, then you get a less powerful one. And that's usually why, I think anyway, they have like different settings, right? They have like a 1 and a 2. Okay. So if you put it on the 1, then it's not going to use 1500 watts. Maybe it only runs at 800 watts, and maybe that doesn't make your hair split or whatever. I don't know. I don't have enough hair to worry about it anymore. Okay. But yeah, so microwaves, same idea. Okay. The ones that we have in the cafeteria, I think, are about 1100 watts, right? So they can, heat stuff up pretty quickly, right? If you had a less powerful microwave, like the one in Mr. Dickey's room, I think it's only like 800 watts, and it's really old, so maybe it's only now 500 watts. If I want to make soup in that, it takes like 7 minutes, right? Whereas if I put it in the 1100 watt one, I can have it done in 3. Okay. So it all kind of, that's where power comes in. Okay. The number of watts tells you how quickly can it do a job. Can Mr. Dickey's microwave make soup? Yes, but it takes longer to do it because it's not as powerful. Okay, everybody got that one? Okay, that's all you need to know about power. After that, you're good. Okay, now we're going to do this tomorrow. Okay, so a couple of specifics here regarding your unit exam. So obviously the unit exam review is at the end of the booklet, okay, of the workbook. right? So you'll see it here on the very bottom of page 11. It's right next to this stuff that's highlighted. These are actually the answers to these extra work energy theorem problems that are here. And so that highlighted stuff goes with these. Don't worry about these graphs. Okay, we never covered force distance graphs because they're not really part of the curriculum anymore. But you actually made one of these back in Science 10. If you did the rubber band lab where you pulled the rubber band with the scale, with the spring scale, okay, you made a force distance graph, and basically what you found was that, okay, so you would have had distance and force, and the graph looked like this, right? Basically what you found was that by calculating the area under the line, you were able to calculate the amount of work done because you multiplied force by distance. Okay? In fact, average force, because you went 1/2 the base times the height, okay, and got the work done in that situation. Again, you don't have to deal with that in Physics 20. That's just what we did in Science 10. Okay, so specifics here. Remembering or quickly reviewing inclined planes, because you know those are my favorite kind of Newton's second law question. Hint, hint. Okay. Anytime I'm doing a Newton's second law question of any kind, I have to remember that there are two ways to calculate net force. Mass times acceleration if I have it, or sum of all forces. In almost every question we did, which method did we use? Well, yeah, or both. In fact, in most of them, we used both, right? Like a question like this could say, all right, there's a 10 kilogram block on this ramp that has, let's say, I don't know, 15 newtons worth of friction, okay, on it. Calculate the acceleration of the block, right? Well, I can't just go mass times acceleration. I don't know what the force is here. Okay, if I want to calculate the acceleration of the block, I have to get the net force. So every time we had an inclined plane, we know that the hypotenuse of the triangle was the force of gravity. Okay, we know that this side of the triangle is the normal force, which we only used if they gave us the coefficient of friction, and we had to calculate friction that way. Okay, and then that this side of the triangle here was F parallel. The angle inside is always the same as the incline, right? So I need to know what F parallel is, because that's the force that always pulls down the ramp, because it is the net force between normal force and gravity. Okay, so in this situation here, this would be 98.1 newtons. Okay, 9.81 times 10. To get this side, it's the opposite side, so I would go sine of 30 times the hypotenuse, which means that this side here would be 49.05 newtons. All right. If I want to find acceleration, I need net force. Can I find net force now? Okay, so now I'm going to use the sum of all forces. What forces am I going to add together? Right, force parallel and force of friction. Why am I not going to include gravity and normal force? Yeah, well, actually, I already did them. Okay, remember, F parallel is already the vector sum of those two forces. Okay, so they've already been accounted for in calculating this, right? That's why I drew them tail to head, right? I drew F normal, then I drew gravity. F parallel is the net force of those two already, okay? That is the most common mistake people make on inclined plane problems, is they factor in, they do sum of all forces, and they do this. They go F parallel plus friction plus gravity plus normal force. Okay, and then they get way too big a number because they have already taken these ones into account. All right, so now I can calculate the net force. Okay, so F net will be 49.05 plus negative 15. Okay, I have to make sure that I have a vector thing here. They're in opposite directions. Okay, so we're going to have 34.05 newtons down the ramp as my net force, and then to get acceleration, it's F net divided by mass. Okay, 34.05 divided by 10 kilograms is 3.4 meters per second squared down the ramp. Okay. Everybody all right with that? Okay. I mean, that's a pretty basic one, but I'm not going to get too much more difficult than that on the unit exam. Okay. As long as you remember how to do inclined planes, you're good. Okay. Any other type of question you guys want to quickly review? No? Okay, so like a vector addition question? Okay. So let's say, all right, so I've got this 20 kilogram block, and it's being pulled east, like due east, with 150 newtons, and it's being pulled, let's say, south of east with 200 newtons. All right. So I want to find the acceleration of the 20 kilogram block. Can I do it with that diagram? No. Okay, now I need to draw this as vector diagram of this. Okay, because right now, I mean, looking at this, I'm pulling it east and south of east. Which way is it going to go? Southeast. Yeah, it's going to go somewhere in between these two, right? That's the direction it's going to accelerate. Well, if I just go like this, that's not what I get. Okay, that's connecting the dots. That's not what we do here, right? So instead, I need to draw a vector diagram of this situation. So I'm going to have my 150 Newton force, and I'm going to have the 200 Newton force. Okay, so now that I've got my vector diagram, my net force is the vector sum of all forces. So that means that that red triangle will get me F net. Okay, and it has obviously an X and a Y component. So really no different than what we would have done in Unit 1 for a displacement question, total displacement question. All right, so I got to find all the x's and y's. So for our first vector there, so we'll say x1 is 150 newtons east, and y1 is 0 because it's due east. Okay, x2, okay, is this side here, so I'll just label it x2. All right, so I've got to find that using trig, so that'll be 200. Cos. It's the adjacent side. Cos of 40 times 200 is 153.21. Okay, obviously you're not going to round until the very end when you do this, but just for the sake of time, I am. Okay, so and then for y2, okay, so that'll be this over here. It's the sine of 40 times 200. Okay, so 128.56 newtons, and that's south, and this one is east. Right now, I can find red x and red y. Okay, red x is going to be 150 plus 153.2. So 0.21 newtons, and red y, there's only one y component, so it's 128.56. Okay, this is east, and this is south. Now that I have the two sides of that triangle, I can find F net, okay, using Pythagorean theorem. So F net will be the square root of 303 squared plus 128 squared, obviously with the decimals in there, and not like what I've done. Okay, so my net force is 329.34 newtons. Right? That's its magnitude. Force is a vector quantity, as is acceleration. Right? So now I need to find theta. Okay, the way I drew my triangle, okay, it's going to be y over x if I'm going to use tan. Okay, so tan to the minus 1 of 128 over 303 will give me my angle south of east. Whoop, what did I miss? I did not put a division thing in there. And now I've screwed it up. All right, so I've got an angle there, 23 degrees. Okay, and that angle is, as I said before, south of east. All right, so now I have my net force and its vector. Okay, to calculate acceleration is F net divided by mass. So 329.34 divided by, what was it, 20 kilograms? Yeah. Divided by 20 will give me my acceleration. All right, so the acceleration is 16 meters per second squared at 23 degrees south of east. Okay, so just vector addition, find x's, find y's. Okay, definitely be able to do that. Okay, any other types of questions you'd like to see? Yeah, a static question. Okay. All right, so you had one like this on your Newton assignments. So let's say we've got this weight here, and it is, let's say 100 kilograms, just so we got a nice round number. Okay, so there's a 100 kilogram weight hanging from these cables. Okay, these cables are attached to different walls, but they both have the same angle between the wall and the cable. Let's say that angle is 40 degrees. Okay, we want to find the tension in these cables. All right, because the cables have the same angles and are the same length, they have the same tension in them. All right, that's the first recognition that we have to make. Their tensions will be identical. How am I going to find this side of the triangle? Or what, like, essentially, what's the net force in this question? Yeah, it's zero. It's not moving, right? The weight is just hanging there. So that means that the downward force of gravity, which is 981 newtons, okay, has to be offset by something. What is it being offset by? Well, actually, there's not going to be any normal force. It's just going to be part of the tension. What part of the tension is going to be offsetting this? The vertical part, right? Each one of these cables, because it's pulling at an angle, has a horizontal component that we can't calculate, and, well, at least not right now, okay, and a vertical component that we can calculate, because we know each cable is holding how much of the 981 newtons? Half of it. Okay, so each one of these cables is holding 490.5 newtons. Because they're identical, I only actually have to calculate one side, and then I know the other. Right, so now I know this side, which is adjacent to the angle I was given. I can now calculate the hypotenuse of the triangle. Right, so the steps, the intuitive steps here are net force is zero. Each cable's holding half the mass, or half the weight, sorry. Right? Once I figure out those two things, then it's just a matter of some trigonometry, and I'll have my final answer. Okay, so to get this, I'm going to go that the cos of 40 degrees is equal to 490.5 over t. So if I want to solve for t, I'm going to cross multiply with the cos of 40, okay, and I'll have that t equals 490.5 divided by the cos of 40 degrees. All right, so there's 640 newtons worth of tension in each cable. Okay. Okay, what else? Huh? Okay, so with Newton's third law, like I said, there's not going to be any problems per se to do with that. Okay, it's mostly going to be like multiple choice situations. All right, so you know, if I hit the wall with 300 newtons of force north, what force will what will the acceleration of my hand be? Okay, well, if I exert 300 newtons worth of force on the wall exerts how much back on my hand? Same, 300 newtons backwards. As long as I know the mass of my hand, I can calculate the acceleration of my hand because I know the force back on. So that would be the extent of the calculating that you would have to do. Yeah. Classic elevator problem, sure. Okay, so a 2 kilogram ball is thrown upward with an acceleration of 6.2 meters per second squared up. I want to find the force that would have had to have been used to throw it. Okay, so right now, I know the acceleration. I know the mass. Okay, and that's it. What does the free body diagram of this situation look like? What force or forces are acting on the ball? Right, applied force and force of gravity. Which of those forces do people most often forget? Actually, that's the one they calculate, but the one they forget is gravity. If I don't outright mention it, people often forget that it's there and assume that only an applied force was acting on this ball, okay, which produces a much different answer. Right. So, what can I calculate with mass and acceleration? Net force. So that should be my first step. Okay, so net force is going to be 2.0 times 6.2. So my net force is 12.4 newtons up. Okay, on here I can calculate the force of gravity because I know that this is 2 kilograms. So this is 19.62 newtons. All right, so I already used one of the two methods to calculate net force. I used mass times acceleration. The question wants me to calculate applied force. Can I use sum of all forces to get the applied force? I can, okay, because F net is the applied force plus the force of gravity. This is why when people forget about gravity, they get this question wrong, because then they just say net force is equal to the applied force, and then they don't get a big enough force. Right? So if I want to calculate applied force, I'm going to subtract Fg over to this side. So I'll have F net minus Fg, which happens to also be negative, okay, equals Fa. So we'll have our 12.4 newtons up minus negative 19.62 newtons, and that'll give us our applied force. Okay, so our applied force there is going to be 32 newtons up. Okay, and if I gave that question on a test, probably a lot of people would forget up, right? You definitely want to remember to put vectors on your answers. Okay, it's very common for people to lose points by forgetting vectors. Okay, much more so actually than significant digits. Okay, more often they forget vectors. Okay, what else? Pulling an object on an angle, yeah. Sorry, I got to kind of half do this one in my head so I don't pick numbers that don't work. I don't want it to accelerate backwards because friction's bigger than forward force. So give me a sec here. I think that'll work. Okay, I want to calculate the acceleration of the 20 kilogram mass. It's being pulled along the table, I hope. I didn't make it too big. Okay, being pulled along the table by an angled force of 160 newtons, 35 degrees above the horizontal. Okay, so what other forces are acting on this? If we have mu, what other force is present? Friction. Yeah. Okay, so I know friction is back here. I don't know what it is yet. I'll be able to calculate in a little bit. Right. I also would have gravity. I would have normal force. Okay, and then I've got this force here, this 160. Since it's moving along the table, I would like to eliminate my angled force by breaking it up into its vertical and horizontal components. Okay, because I know this thing is moving along the table, I know the net force vertically is what? No, what is the F net vertically? Like what number is it? 0, right? It's not moving vertically, right? The question said it's being pulled along the table, so it's not moving vertically. Okay, so I need to calculate what F vertical is. I need that because I need to know what Fn is in order to calculate this. Okay, I can't calculate the force of friction without F normal. Okay, so we have force vertical here, and we have force horizontal here. Right? I need to know what those are because, especially force horizontal, because the box is moving horizontally across the table. Okay, so the force horizontal is the adjacent side. So that'll mean cos of 35 times 160 is 131.06. Okay, and the vertical part of that, whoop, is 91.77. Okay. Force of gravity I can also calculate, okay, by just going m times g. All right, can I calculate normal force now? Right, I can calculate it because I know that Fg, Fv, and Fn all add up to 0. Right, so all I have to do is take the 196 and subtract that, and I'll have what the other one is. So okay, so my normal force is 104.43. Okay, now that I have that, I can calculate the force of friction. Okay, so my force of friction is 36.34 newtons. Okay, so now I don't need this force anymore, I don't need that force anymore, don't need this force anymore, and I don't need that force anymore. Okay, I know that the box is only moving along the table horizontally. The only two forces now that matter are the forces acting along the table, friction and the horizontal component of the pulling force. Okay. All right, so I'm going to take that 131.06 and subtract the force of friction. That will give me my net force. Okay, and the reason I canceled off all these other forces is I already taken them into account. I know that the three vertical ones add up to 0, so I don't need them. Okay, and I don't need this because I've already taken it into account as well. Okay, so 131.06 minus our force of friction gives us a net force of 94.718 newtons. If I divide that by the mass, the acceleration of that 20 kilogram box is going to be 4.7 meters per second squared along the table, forwards, something, some vector like that. Okay. We did probably 3 like that in class already. Okay. I could also make this a 2-part question by now asking you if the box is dragged 15 meters, how much work is done? Okay, and then I would take my force and multiply by my distance, and I would have the amount of work done, or something like that. Yeah, you would get part marks for method. Yeah, like you wouldn't just get like on a part B if you got the answer for part A wrong and B depended on it, you'd still get marks for method in part B, but not for your final answer because you wouldn't be able to get it right. Yeah. No, I don't believe it's fair to say all your mark in part B depends on if you did A right. Okay? Then I might as well give you a multiple choice test that's right minus wrong. You don't want that. That sucks. I had many of those in university. Multiple choice, right minus wrong. So you had a question, and then it was A, B, and C, and A, B, C, and D, and A, B, C, and D were to do with these other 4 options, 1, 2, 3, and 4. So you'd read the 4 options, and then A would be 1 and 4, B would be 3 and 2, and 1 only. So you had to decide which ones of these were right, so you could answer the first part, and then any ones you got wrong were subtracted from the number you got right. Yeah. It was like, okay, so if I do 4 questions that I'm sure of, I'll get 4 out of 20. If I do 2 more that I'm not sure of and I get them wrong, I'll get 2 out of 20. It really makes you second guess everything. It's psychologically awful. So I won't do that to you. Okay, any other ones you want to go over? Okay, conservation of energy. That's supposed to be a toboggan, by the way. Okay. Look that from the side. Don't let your kids go on this hill. It's a bit crazy. 26 meters per second is like 100 kilometers an hour. So, okay. All right, I want to calculate the initial height of this toboggan on the hill. Okay. Is it okay that it didn't give you the mass of the toboggan? Yeah, it's fine, because it'll cancel. We don't need it, but I would give it to you on a test. I'd tell you it was 1,000,000 kilograms just to mess with you. But it wouldn't matter. It would all work out. All right, so we know that the energy at the top is equal to the energy at the bottom because somewhere in this question it would have said friction is not a factor, or this is a frictionless hill, or gravity is the only force doing work, or something like that. Okay. All right, so do I have kinetic energy at the top? Do I have potential energy at the top? Being at the top kind of gives you potential. Okay, and at the end, do I have both kinds as well? Yeah, I'm still 5 meters above the bottom and moving at 26 meters per second. So I would have potential initial plus kinetic initial equals potential final plus kinetic final. And that's going to mean m times g times h initial plus 1/2 mv initial squared equals m times g times h final plus 1/2 mv final squared. Okay, what am I looking for? HF or HI? HI, right? I'm looking for the initial one. All right, so I'm looking for this, which means I need to start moving things around. First thing I want to do is get rid of the thing I don't need / don't have, okay? And that's the mass of the toboggan. Now I'm going to subtract the kinetic over to this side, so I'm left with this. GHI equals GHF plus 1/2 VF squared minus 1/2 VI squared. I'm looking for H, so I need to divide both sides by G. Again, be careful here. G does not cancel, even though it's on the top and the bottom. I'm doing an operation on the top first. Okay, so that'll give me my initial height. So initial height will be 9.81 times 5 plus 1/2 times 26 squared minus 1/2 times 6 squared divided by 9.81. Okay, and then divide by 9.81. All right, so the top of the hill is 38. I guess we only have two significant figures here, 38 meters. Okay. Now, as a part B to that, I could say that at the bottom of the hill, the ground flattens. Okay, so let's say at the bottom of the hill, it does this and the ground flattens, and there is now, let's say, a force of friction of 200 newtons. Okay. And let's say, in this case, I would have given you the mass of the toboggan because it is something you're going to need. So let's say, the toboggan is, including rider, 50 kilograms. Okay, so I would tell you there's 200 newtons of friction at the bottom. How far does the sled slide before coming to a stop? Okay, so how much energy does it have at the bottom before it starts to slow down? We don't really know the number because we never calculated it, but it's the same as it is here and here. Agreed? So can I calculate what that number actually is really quickly? I just have to add the potential and the kinetic together. Okay, so I'll figure out what it is quickly by going 50 kilograms times 9.81 times 5 plus 0.5 times 5 times 26 squared. All right, so there's the amount of mechanical energy. And when I was at the bottom, it would all be kinetic, okay? But I didn't have the very bottom. I had 5 meters from the bottom. Doesn't matter, okay? That's how much energy, mechanical energy there is. In order to stop, what has to happen to all that energy? It has to be lost, right? Friction has to turn it into other things, sound and heat and light and whatever else, all right? So if I want to end up having no energy, I have to have friction do 4,142.5 joules worth of work. Everybody okay with that? Okay. So here's where this becomes a work energy theorem question. Work's a change in energy, and work is force times distance. I need to change my energy by 4,142.5 joules. Okay, because that's how much energy I have at the bottom, and I want to end up having none. Right? So I have to change my energy by that many joules. Since friction is the only force available to do that, I can calculate how far I would slide before stopping by dividing both sides by that only force. Okay. All right, so I would slide just under 21 meters before coming to a stop. All right, so you see how I can turn, like I can put a part B, I can say one concept in part A and the second concept in part B, okay, and work them together. Okay, any other questions? Like with a pulley or like a Newton's third law system? Okay, I'm not going to have any of those on the test, so I'll save us both some time. Okay. Okay. What else, guys? Okay. Well, if there aren't any more questions, my suggestion to you would be you have 7 old exam questions in that dynamics review that you could probably work on for the last 10, 12 minutes of class or so. Okay. If there are more questions that come up, just ask and we'll go over them.